Okay, hi everyone, welcome to this live stream. Today I want to discuss Windows Server 2003 administration. So just click here, share screen, and here we go. So chapter 1, Understanding Windows Server 2003 Networking. Microsoft has put an immense amount of time and effort into building Windows Server 03. It's not fair to say that this operating system is an entirely new product because it still retains a great deal of the core code from Windows 2000 and even Windows NT, Internet Information Server and Exchange Server. Windows Server 2003 is large, complicated, and very powerful operating system. To use it effectively, you have to understand how it works and how to make it do what you want it to do. This book is a study guide for implementing, managing, and maintaining a Microsoft Windows Server 2003 network infrastructure exam. So it makes sense to lead off with a discussion of the network protocols included in Windows Server 2003, what they're for, how they work, and what you can do with them. Having a good frame of reference helps when comparing network protocols. To establish such a frame, this chapter will begin with the Open Systems Interconnection OSI network model, a sort of idealized way to stack various protocols together. So the OSI model, the International Organization for Standardization, ISO, began developing the Open Systems Interconnection OSI reference model in 1977. It has since become the most widely accepted model for understanding network communication. Once you understand how the OSI model works, you can use it to compare network implementations on different systems. When you want to communicate with another person, you need to have two things in common: a communication language and a communication medium. Computer networks are no different. For communication to take place on a network composed of a variety of different network devices, both the language and the medium must be clearly defined. The OSI model and networking models developed by other organizations attempt to define rules that cover both the generalities and specifics of networks, how network devices contact each other, and if they have different languages, how they communicate with each other, methods by which a device on a network knows when to transmit data and when not to, methods to ensure that network transmissions are received correctly and by the right recipient. However, how the physical transmission media is arranged and connected, how to ensure that network devices maintain a proper rate of data flow, how bits are represented on the network media. The OSI model isn't a product, it's just a conceptual framework you can use to better understand the complex interactions taking place among the various devices on a network. It doesn't do anything in the communication process. Appropriate software and hardware do the actual work. The OSI model simply defines which tasks need to be done and which protocols will handle those tasks at each of the 7 layers of the model. The 7 layers are as follows: application layer, presentation layer, session layer, transport, network, data link, physical. Each of the 7 layers has a distinct function which we'll explore a little later in the chapter. Protocol stacks. The OSI model splits communication tasks into smaller pieces called subtasks. Protocol implementations are computer processes that handle these subtasks. Specific protocols fulfill subtasks at specific layers of the OSI model. When these protocols are grouped together to complete a whole task, the assemblage of code is called a protocol stack. The stack is just a group of protocols arranged in layers that implements an entire communication process. Each layer of the OSI model has a different protocol associated with it. When more than one protocol is needed to complete a communication process. The protocols are grouped together in a stack. An example of a protocol stack is TCP/IP, which is widely used by Unix and the Internet. The TCP and IP protocols are implemented at different OSI layers. Each layer in the protocol stack receives services from the layer below it, and it provides services to the layer above it. It can be better explained like this. Layer N uses the services of the layer below it. Layer N-1 provides services to the layer above it, layer N+1. For two computers to communicate, the same protocol stacks must be running on each computer. Each layer on both computer stacks must use compatible protocols in order for the machines to communicate with each other. The computers have different operating systems and still be able to communicate if they are running the same protocol stacks. For example, a DOS machine running TCP IP can communicate with a Macintosh machine running TCP IP, see figure 1.1. So you see here, figure 1.1, each layer communicates with its counterparts on the other network hosts, the physical layer. The physical layer is responsible for sending bits from one computer to another. Physical layer components don't care what the bits mean. Their job is to get the bits from point A to point B, and using whatever kind of optical, electrical, or wireless connection that connects the points. This level defines physical and electrical details, such as what represents a 1 or a 0, how many pins a network connector will have, how data will be synchronized, and when the network adapter may or may not transmit the data, see figure 1.2. The physical layer makes a physical circuit with electrical, optical, or radio signals. The physical layer address all the minutiae of the actual physical connection between the computer and the network medium, including the following: network connection types, including multi-point and point-to-point connections, physical topologies, or how the network is physically laid out, bus, star, or ring topologies, which analog and digital signaling methods are used to encode data in the analog and digital signals. Bit synchronization, which deals with keeping the sender and receiver in sync as they read and write data. Multiplexing, or the process of combining several data channels into one termination, which prevents signals from reflecting back through the cable and causing signal and packet errors. It also includes the last node in a network segment, the data link layer. The data link layer provides for the flow of data over a single physical link from one device to another. It accepts packets from the network layer and packages the information into data units called frames. These frames are presented to the physical layer for transmission. The data link layer adds control information such as frame type to the data being sent out. This layer also provides for the error-free transfer of frames from one computer to another. A cyclical redundancy check, CRC, added to the data frame can detect damaged frames, and the data link layer in the receiving computer can request that the CRC information be present so that it can check incoming frames for errors. The data link layer can also detect when frames are lost and request that those frames be sent again. In broadcast networks such as Ethernet, all devices on the LAN receive the data that any device transmits. Whether a network is broadcast or a point-to-point is determined by the network protocols used to transmit data over it. The data link layer on a particular device is responsible for recognizing frames addressed to that device and throwing the rest away, much as you might sort through your daily mail to separate good stuff from the junk. Figure 1.3 shows how the data link layer establishes an error-free connection between two devices. So here we have data 1 physical layer, data 2 link layer, and so on and so forth. The Institute of Electrical and Electronic Engineers, IEEE, developed a protocol specification known as IEEE 802.x. 802.2 is the standard that divides this layer into two sublayers. The MAC layer varies for different network types and is described further in standards 802.3 through 802.5. As part of the specification, which we know today as Ethernet, the data link layer is split into two sublayers. The logical link control LLC layer establishes and maintains the logical communication links between the communicating devices. The media access control MAC layer acts like an airport control tower. It controls the way multiple devices share the same media in the same way that a control tower regulates the flow of air traffic into and out of an airport. Figure 1.4 illustrates the division of the data link layer into the LLC and MAC layers. So figure 1.4, the IEEE split the ISO data link layer into the LLC sublayer and the MAC sublayer. So you see here, physical layer and the data link layer, media access control sublayer, logical link control sublayer. The LLC sublayer provides service access points, SAPs, that other computers can refer to and use to transfer information from the LLC sublayer to the upper OSI layers. This is defined in the 802.2 standard. The MAC sublayer, the lower of the two sublayers, provides for shared access to the network adapter and communicates directly with network interface cards. Network interface cards have a unique 12-digit hexadecimal MAC address, frequently called the hardware Ethernet address, assigned before they leave the factory where they are made. The LLC sublayer uses MAC addresses to establish logical links between devices on the same LAN. The network layer handles moving packets between devices that are more than one link away from each other. It makes routing decisions and forwards packets as necessary to help them travel to their intended destination. In larger networks, there may be intermediate devices and sub-networks between any two end systems. The network layer makes it possible for the transport and network layers above it to send packets without being concerned with whether the end system is on the same piece of the network cable or on the other end of a large wide area network. To do its job, the network layer translates the logical network address into physical machine addresses, MAC addresses, which operate at the data link layer. The network layer also determines the quality of service, such as the priority of the message and the route of the message will take if there are several ways the message can get to its destination. The network layer may also split the network layer also may split large packets into smaller chunks if the packet is larger than the largest data frame. The data link layer will accept. The network reassembles the chunks into packets at the receiving end. Intermediate systems that perform only routing and relaying functions and do not provide an environment for executing user programs can implement just the first three OSI network layers. Figure 1.5 shows how the network layer moves packets across multiple links in a network. So you see here your router, physical layer, data link layer, and network layer. The network layer performs several important functions that enable data to arrive at its destination. The protocols at this layer may choose a specific route through an inter-network to avoid the excess traffic caused by sending data over networks and segments that don't need access to it. The network layer serves to support communication between logically separate networks. This layer is concerned with the following: addressing, including logical network addresses and service addresses, circuit, message, and packet switching, route discovery and route selection, connection services, including network layer flow, network layer error control, and packet sequence gateway services. In Windows Server 2003, the various routing services for TCP/IP, AppleTalk, and Internetwork Packet Exchange, Sequence Packet Exchange, IPX, SPX, perform network layer services, managing IP routing for more of these. In addition, the TCP/IP, AppleTalk, and IPX stacks provide routing capacity for those protocols. The transport layer. The transport layer ensures that data is delivered error-free, in sequence, and with no losses or duplications. This layer also breaks large messages from the session layer into smaller packets to be sent to the destination layer, and reassembles packets into messages to be presented to the network layer. The transport layer typically sends an acknowledgement to the originator for messages received, as in figure 1.6. So figure 1.6, the transport layer provides end-to-end communication with integrity and performance guarantees. The session layer. The session layer allows applications on separate computers to share a connection called a session. This layer provides services such as name, lookup, and security that allow two programs to find each other and establish the communication link. The session layer also provides for data synchronization and checkpointing, so that in the event of a network failure, only the data sent after the point of failure would need to be resent. This layer also controls the dialogue between two processes and determines who can transmit and who can receive at what point during the communication. See figure 1.7. Figure 1.7, the session layer allows applications to establish communication sessions. The presentation layer. The presentation layer data between the formats the network requires and the format of computer expects. The presentation layer performs protocol conversion, data translation, compression and encryption, character set conversion, and the interpretation of graphics commands. The network redirector, long part of Windows networking, operates at this level. The redirector is what makes the files on a file server visible to the client computer. The network redirector also makes remote printers act as though they were attached to the local computer. Figure 1.8 shows the presentation layer's role in the protocol stack. Figure 1.8, the presentation layer allows applications to establish communication sessions with each other. The application layer. The application layer is the topmost layer of the OSI model, and it provides services directly, supports user applications such as database access, email, and file transfers. It also allows applications to communicate with applications on other computers as though they were on the same computer. When a programmer writes an application program that uses network services, this is the layer the application program will access. For example, Internet Explorer uses the application layer to make its request for files and web pages. The application layer then passes those requests down the stack, with each succeeding layer doing its job, as in figure 1.9. Figure 1.9, the application layer is where the applications function using lower levels to get their work done. Communication between stacks. When a message is sent from one machine to another, it travels down the layers on one machine and then up the layers on the other machine, as shown in figure 110. As the message travels down the first stack, each layer it passes through except a physical layer adds a header. These headers contain pieces of control information that are read and processed by the corresponding layer on the receiving stack. As the message travels up the stack of the other machine, each layer removes the header added by its peer layer and uses information it finds to figure out what to do with the message content. See figure 1.11. As an example, consider the network we're using while writing this book. It's a TCP IP network containing several Windows 2000, Windows Server 2003, Macintosh, and Windows NT machines, all connected using the TCP IP protocol. When we mount a share from our Windows Server 2003 file server on the Mac desktop at layer 7, the Mac Finder requests something from the Windows Server 2003. This request is sent to the Mac's layer 6, which receives the request as a data packet, adds its own header, and passes the packet down to layer 5. At layer 5, the process is repeated and it continues until the packet makes it to the physical layer. The physical layer is responsible for actually moving the bits across the network wiring in the office, so it carries the request to a place where the Windows Server 2000 machine can hear it. At that point, the packet begins its journey up the layers on the Windows Server 2003 file server. The header that was put on at the data link layer of the Mac OS is stripped off at the data link layer on the Windows Server 2003 machine. The Windows data link layer driver performs the tasks requested in the header and passes the request to the next higher layer. This process is repeated until the Windows Server 2003 file server receives the packet and interprets the request. The Windows Server 2003 would then formulate an appropriate response and send it to the Mac. So here we have figure 110, traffic flows down through the stack on one computer and up the stack to the other. Figure 1.11, all packets flow up and down the stacks. Each layer adds and removes necessary control information. So I'm going to leave it here today for this video. If you like listening, please consider sharing, and thanks for spending the time with me, and have a nice evening.